Hello, this is Mr. Gilmore with the 3.4 side-side-side congruence lesson. In this lesson, we're going to prove our next triangle congruence principle. Now, unlike the side angle side, which was a postulate, side-side-side will actually be a theorem. And now we have enough tools in our toolbox to prove the side-side-side. We've been seeing how our proofs have evolved very quickly, involving construction, and now we'll actually have to use the properties of construction. The theorem we've proven this chapter, which is isosceles triangle theorem, and the use of our very first triangle congruence postulate side angle side to then prove side side side. So let's go ahead and take a look at what is side 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 congruence state. It states very simply that if the sides of one triangle equal the sides of another, then those two triangles are congruent to each other. Essentially, think about our magic number. Our magic number is 3. We need 3 things of one equal to 3 things of the other. Now, it can't just be any 3 things. In this case, we're looking at the 3 sides of one triangle equal to the 3 sides of the other. Once we have that, we will have congruence. Now, I have an illustration of when we have two triangles with the sides of one equal to the sides of the other, what is then the conclusion? So here's what this looks like. If we have these two triangles such that all 3 sides of the first are equal to all 3 sides of the second, then what may we claim? We may claim that the two triangles are in fact congruent, meaning all the corresponding parts are in fact equal. In other words, we can then take this congruence and show that all the angles that correspond are equal, and we have a reason for why that is. CPCTC. That the corresponding angles of congruent triangles are in fact congruent. So now, once we've proven that the two triangles are congruent with the side, we can show all the angles are congruent. So now our goal is to prove that the side congruence theorem is true, right? We've got a conditional. Let's prove that this conditional is in fact true. So let's do the proof setup. In our given, we establish, let's start with two given triangles, triangle ABC and triangle RST, such that the 3 sides of the first are equal to 3 sides of the second. So I have AB equals RS, that's been marked in our diagram as single hash marks. BC equals ST, those are our double hash marks, and AC is equal to RT, that's our triple hash marks. We're going to now prove that these two triangles are in fact congruent. And where we actually start with this proof is with a series of constructions. So as of right now, there's really not much other than what we're given that links the two triangles together. So what we're going to do is we're going to build a triangle that does link these two triangles together. So here's where we start. We are going to start using the protractor postulate. The protractor postulate says this: we are allowed to measure and make measure of angles. So what I'm going to do is come over here to my second triangle, and I'm going to measure out the angle R. So I know R has a certain angle measure to it. And then using the side of our triangle in our first triangle, side AC, I'm going to produce a ray from vertex A out of that side such that the angle created here is also the exact same measure as angle R. And I'm allowed to do that. That is using the protractor postulate. I'm actually using both of its clauses. I can measure and make measure. So that's our very first construction, actually producing this angle such that it's equal to angle R. The next step is we can use the ruler postulate. The ruler postulate also has two clauses. It can measure and make measure, which then means I'm going to measure out the segment RS. RS has a certain measure to it. I'm going to measure it and then duplicate that measure on the ray we just created. So I'm going to then place a point M on that ray such that AM and RS are equal in measure. So notice that we've got these single hash marks here because I can duplicate the segment measure. So I end up truncating my array at point M, so I don't need the rest of that. I'm just going to have it stop at point M. Our last construction, or I should say, our second to last construction is very simple. We then just connect point M to point C. Now notice that what we've done in the second to last step, We have then created a third triangle, triangle AMC. As it turns out, that's going to be the bridge that helps connect these two triangles ABC and RST together. But there is one more construction we're going to make, and this is where I usually get some heads that turn and go, what? Why? We're going to connect point B to point M. So by doing this, so you notice that I put a dashed line in there, dash segment. I've now constructed point B from point B to point M, another segment. And I always get a question of why are we doing this? We're going to see the reason why we do this as we then begin our proof. So now this is the end of our construction phase. It's now set to move into our proof phase of how can I now reach the conclusion that triangle ABC is congruent to triangle RST. Now this is a proof overview. This is actually not the entire proof. This is merely just going to give you an idea of where the proof goes. So I'm going to walk you through this proof overview, but on the problem set, basically on the worksheet, you're going to fill in the detailed version of this proof. But you're going to notice that the detailed version simply is going to follow the same overview that we're doing in this slide here. So I have our diagram below, but there are 5 steps we're going to answer. Okay, I've essentially provided you the statements. You're going to help me find then the reasons. So yes, again, it's kind of awkward. We connected point B to point M, but you're going to see here very quickly that it's something special we end up doing. So the very first statement that I can make right after my congruence or right after my construction phase is that I can call a triangle AMC congruent to triangle RST. Let's take a look. Here's triangle AMC and triangle RST. I know those two triangles are immediately congruent. And why is that? We'll take a look at what we have. We're given that AC is equal to RT. That's what we're given. That's one side. We constructed angle A here to be the same measure as angle R, and we constructed AM to be the same measure as RS. So what does that mean to us? That means we have side, angle, side. So I can call those two triangles congruent by side, angle, side congruence. Now, immediately following congruence, we're allowed to then use CPCTC to claim that we have equal things. So I'm going to claim now that MC and ST are equal because we now have corresponding parts of congruent triangles to be congruent because we established congruent triangles. This is where the important part of connecting point B to point M is. So what or why is that important we connect it? Because now we have in our diagram 2 isosceles triangles. 2 isosceles triangles. Let me point out the first one. Where are those isosceles triangles? Well, since AB is equal to RS and RS is equal to AM, then what do I know about AB and AM? They are provably equal, which means I have an isosceles triangle here. Note then, do you see the importance of having BM listed in there? Because I produce one isosceles triangle. But there's actually a second one. Thanks to our first 2 steps, we proved that MC is equal to ST, and ST is also equal to BC, which means BC and MC are equal to each other. That is a second isosceles triangle. BM is that common side of both. So where are the 2 isosceles triangles? They're in that construction phase that we did off of triangle ABC. So what can follow then from isosceles triangles? It follows then that we know their base angles are equal. So I can claim that angle, I'm going to actually clear this up a little bit. I can claim that angle ABM and angle AMB, they're equal to each other. I actually should do a double hash mark there. And I can also claim that angles CBM and CMB are also equal. That is an important phase because note now that I have these 2 pairs of equal angles, but more than that, I have two pairs of equal adjacent angles. What happens if I took this angle measure here, let's call this angle 1, and added it to angle 2? So I'm taking these two angles here and add them together. Let's take here angle 3 and angle 4 and add those two angles together. What happens when I add equals to equals? Oh, that's right. I get equal things. So what we can then prove here is that not only do we have those base angles equal, but we can prove that the entire angle here of angle B and the entire angle here of angle M, they have to be equal to each other. So we know that we know that these two angles here are equal to each other. That's important because now we have another pair of congruent triangles. So it comes right out of step 3 into step 4. So in step 3, we used the ITT. So yes, you will use ITT as a reason. And actually, you're going to use it 2 times because we ran into 2 isosceles triangles. But now I can claim that I have another pair of congruent triangles. I can claim triangle ABC and triangle AMC are congruent. Here's why. Look, AB and AM, they're equal. BC and CM, they're equal. And we just proved that their included angles are equal. So what do we have going for us? We have side, angle, side. Side, angle, side. So that is why we know that we have a second pair of congruent triangles, which then we can follow into the very last step, which is I now know that triangle ABC and triangle RST are in fact congruent to each other. And here's why. In my step 1, I have triangle AMC congruent to triangle RST. And in step 4, I have triangle AMC also congruent to triangle ABC. Well, what do we call two triangles that are congruent to the same third triangle? We also call those two triangles congruent. Why? Because of our relationship of transitivity of congruence. That is something we saw in a previous worksheet where we proved that the relationship of transitivity, the relationship of congruence also applies in the property of transitivity. So now there is our proof. We now have side, side, side as a theorem that proves that two triangles are in fact congruent. Now on the problem set in the worksheet, you're going to find the more detailed version of this theorem, okay, the more detailed version of this proof. So I've provided the statements just like I did here. You're going to provide the reasons. To finish off today's lesson, we're just going to look at a very simple proof of side, side, side. So take a moment to draw your diagram, write down the given and proof statements, and then we'll jump into a proof. Now this proof really is very simple. I'm going to go ahead and set up my 2-column. So I'm going to prove that these two triangles are congruent. Step 1 is always my given. I have a pair of equal sides, AB is equal to AD, and I have a second pair of equal sides, BC is equal to CD. So I already know I have two sides of one triangle equal to two sides of another. I wonder if I can find a third pair of sides. I can. Those triangles that we see here share a common side. We love common sides. Why? Because they give us equal things, and equal things lead us to congruence. So AC is equal to AC. Why? That's because of reflexivity of equality. Everything is equal to itself. Hey, now, do all three sides of one equal all three sides of the other? Yes, indeedy, which means we can call triangle ABC congruent to triangle ADC by a very simple fact of side-side-side congruence. So there we have it, a very simple proof using the side-side-side congruence within inside of our proof. Please be sure to be working on the homework assignment, okay? If you do actually have any questions over the side-side-side angle, or side-side-side congruence proof, please email me. I would love to get back to you and help you through that. With that, be good and do good.